So general formula for writing olivine would be Mg, comma, Fe with a subscript 2, and then SiO4. That's a little bit sloppy of an F. Let's neaten that up a little bit. So this formula means when we have that comma there that we could take 2 each of any of these. And this olivine has complete solid solution between magnesium and iron components, so we can take them in any proportion we like. For example, we could take the composition, a specific composition, as say Mg 1.5, Fe 0.5, SiO4. So long as these fellows sum to 2, we'll take the fancy way of writing that. We'll use the Greek summation letter, sigma, and that sum is equal to 2, 1.5 plus 0.5, and that satisfies this criterion here. And so we have this kind of formula. We don't have to write it this way. When we write this, this is really just a recipe. There's nothing special about the particular values that we use except for their absolute proportions. So we could rewrite this, if you don't like fractions, we can multiply the whole thing by 2 and equivalently write this as, let's say, Mg3 Fe Si2O8. So we could write it on the basis of 8 oxygens instead of 4 oxygens. That's very untypical, though. We would not usually write it that way. But as you can see, this really holds the same proportions. These are really the same formula. It's the same recipe. This recipe just makes twice the amount of this guy. Well, we'll use this guy here. Let's say we want to use this phase diagram from the online textbook of Dexter Perkins to figure out what temperature this particular composition of olivine would begin to melt. So when would it begin to melt based on this composition here? Well, if we take a look at the proportions of the ions, we have a total of 2. So what is the fraction of magnesium? The fraction of magnesium is equal to 1.5 out of 2 equals 0.75. So magnesium atoms are 75% of this particular mineral. And if we look at the fraction of iron, it would be a similar kind of calculation. We'll take 0.5. It's half, or excuse me, not half, it's 0.5 over a total of 2 cations that are in this octahedral position, and that comes out to 0.25. So if we write the Mg, the pure Mg fellow as this, Mg2SiO4, this is equal to forsterite, and then Fe2SiO4 is the mineral phthalite, and we're being consistent but writing these all on a 4-oxygen basis, then we could say that this is 75% of this fellow here, and this is 25% of this fellow here. So we have something that is molecular, on a molecular basis, 25% phthalite and 75% forsterite. So does that mean that we can come over to this phase diagram here and then plot these numbers? Well, not so fast. So take a look at this. This is the weight percent phthalite, not the molecular percent or atomic percent. It's the weight percent of phthalite. So we have 25% phthalite here. We could start out with phthalite. It starts over here at 100, and from left to right it goes down to 0. So 25% would be about there, but that's only on a molecular basis. So this is not the correct place to plot this particular mineral composition. We need to convert this to a weight percent phthalite. So how would we do that? Well, we would take the molecular weights of forsterite and phthalite. So for forsterite, let's write the molecular weight here. The molecular weight is about 140.7 grams per mole. And then for phthalite, the molecular weight is about 203.8, also in units of grams per mole. So if we want to get the weight percent of phthalite, well, we can get the weight percent of both of these by taking the molecular proportions and multiplying them by these weights. So we will take this fellow here and multiply it by 0.75. We have 75% atomically forsterite, so we'll multiply that by the weight. And we'll do the same thing here. We'll take 203.8, those are just ditto marks. This is also grams per mole, and we'll multiply that by 0.25. So for this top one over here, we'll get a value of 105.5 0.525, and then for phthalate, so that is the weight of forsterite, and then for phthalate, we would get the number 50.95. So that would be the value for phthalate. If we want the weight percent, we could sum these two numbers. The total weight in the system, as we've calculated, is 156.475. So here we're just taking the weights of forsterite and phthalate and adding them together. So what would be the weight percent of phthalate? That would be the amount of phthalate, 50.95, multiplied by 100, since we want it in a percent rather than a fraction. And we'll divide that by 156.475, the total weight in our system, which is here. So that is the total weight as we've calculated here. And this comes out to about 32.6 weight percent for phthalate. And if we've done this calculation correctly, there's only two components, so the amount of forsterite by weight percent should be 100 minus this. I'll leave that calculation for you. It should come out something close to 67.4 weight percent. Now we only need this fellow over here. Remember, we needed the weight percent phthalate to plot on this scale here, and that weight percent, 32.6, would plot, well, there's 30, so 32.6 would be about over here. You could see that it is displaced by maybe just a small amount from the incorrect placement over here, but it will make a big difference in terms of the temperature. We will get a temperature. I'm going to try to draw a vertical line here to hit the solidus, and then try to draw a horizontal line across to reach the temperature scale. And these are sloppy enough that I don't know if it's going to be useful to actually read off the precise numbers. But as you can see, the temperature that we would get by taking the correct value, the weight percent value, is going to be different from what we would have gotten had we incorrectly taken the 25 mole percent and plotted it on this weight percent phthalate. So when we're doing these kinds of calculations, it's very important to look at what kind of scale, both molecular percents and weight percents, are used. And so it's important to sort those out and make sure you're plotting the right one if you want to estimate a melting or vaporization temperature of some kind of compound.